Okay, this is a fun physics problem, and I'm going to do it in multiple ways, but let's just get into the problem. The idea is that there are two asteroids in space, Asteroid A and Asteroid B, and there's no other gravitational objects near them. But there is a gravitational interaction between the two asteroids, and it pulls them together. So they start from rest, and they start a certain distance away. When they touch, how fast are they going? Okay, and so then I have, they start 100, I just pick some values. They start 100 meters apart. This is a 10 meter radius asteroid. That is a 6 meter one. And then I calculate their masses 1.37 times 10 to the 7th, 2.6 times 10 to the 6th. The end. How fast are they going? Okay, let's solve this problem the easiest way possible. And that will give us a good starting value. And then I will solve it in a more complicated way, and then I'll model it numerically. So I'm going to do three things. So let's assume. So if you look right here, A has a mass of 1.3 times 10 to the 7th. B is 2.6 times 10 to the 6th. So, I mean, that's a bit more, right? It's a bit more mass of A is. Let's just assume A is stationary. That will make the problem much easier, and you'll see why in just a second. So if that's the case, now I need to say, well, how am I going to solve this problem? I'm going to use the work energy principle. Work is a change in energy. Why? Well, because if I don't care about the time, and I do for a little bit, but if I'm just looking at the velocity at the end compared to the beginning, you see I have a change in position. Whenever you have a change in position and you don't have a change in time, then you should automatically start thinking, hey, maybe I should use the work energy principle. And so I'm going to use the work energy principle. And with that, the first thing we need to do is declare our system. So what is the system that we're going to look at the change in energy for? And it's going to be the system consisting of both asteroids. Because if I do that, then there's some really nice things that happen. Number one, there's no external forces on the system, so the work is zero. So the system is both A, let's just call it A and B. So in that case, the work is 0 joules. There's no interactions with the outside. Also, I can say the types of energy are going to be the kinetic energy, 1/2 mv squared, and the gravitational potential energy, negative g ma mb over r. That's the gravitational potential energy. I derived that in a previous video. If you want that, I'll put the link down below. Unless I forget, then I won't. So let's go ahead and write out our work energy equation going from, we'll call this positions 1 to positions 2. So this will be VA1, VA2, VA1, VB1, VA2, VB2. Okay. So the work is 0, and that's going to be the change in kinetic energy of object A plus the change in kinetic energy of B plus the change in gravitational potential energy. Now, there's only one potential energy term. Don't try to give it two, right? Because the potential energy is a term due to the work done by the interaction between these two, and there's only one interaction, so there's one potential. Now, I already said, if we're assuming A is stationary, then the change in kinetic energy of A is 0. So that means I get the following. 0 is the change in kinetic energy of B, so it's going to be KB2 minus KB1 plus U2 minus U1. Let's go ahead and put an expressions in for this. Oh, and this is 0, right? The initial kinetic energy for object 1, B, is 0. They both start from rest. So I get 1/2 mb VB2 squared. That's the final kinetic energy of the asteroid B. And then I have minus G MA MB over R2 plus G MA MB over R1. Notice that this is plus a negative, so that's negative. And this is minus a negative, so that's plus. Now I want to solve for VB2, so I'm going to go ahead and add this and subtract that from both sides. I get 1/2 MB VB2 squared equals G MA MB over R2 minus G MA MB over R1. So I added that to both sides, so it became positive. I subtracted that from both sides, it became negative. Now I'm going to multiply both sides by 2 and divide by MB. So I get VB2 squared is going to be equal to 2G MA. I'm factoring out the MA. The MB is canceled. And that's all 1 over R2 minus 1 over R1. And then I just need to take the square root of that. I did that right? I always get these backwards. So let's see, 1 over R2. R2 is smaller. Yeah, so this is going to be a bigger number. Okay, I just want to make sure I didn't take the square root of a negative number. So I get VB2 is going to be the square root of 2G MA 1 over R2 minus 1 over R1. Let's go ahead and calculate that number. I'm going to calculate that in Python, just because we're going to be using Python later anyway. I want to put all these numbers in. Let's see what the final velocity for B2 is. So switching over to Python. Hello, Python. Make this a little bit bigger. Bigger. That's good. I like it big. Okay, so I already have G, I have R1, R2, MA, MB, and so you see my expression just has those same values in it. So I'm just going to calculate, I'm going to say VB2 equals the square root of 2 times G times MA. Notice that MB doesn't show up in there, because if I hold MA stationary, it doesn't really matter what the mass of that is, because I'm assuming that it's just insignificant compared to A. Times 1 over R2 minus 1 over R1. I guess we should check the units on this too. I'll check that in a second. And then print. VB2 equals VB2 meters per second. Run it. Okay, so I get 9.5 times 10 to the negative 30 meters per second, which is not very fast. Okay, that's like 9 millimeters per second. Really, really slow. Okay, let's go back and let's check the units, and then let's do this problem again. So let's just check the units. So first of all, G has units of Newton meters squared per kilogram squared, right? Because if I multiply the gravitational force, I'm thinking of the gravitational force, F equals G M1 M2 over R squared. So I have to get that in terms of newtons. And a newton, 1 newton is equal to a kilogram meter per second squared. So if I put that in up here, I get G in units of kilogram meters cubed. Okay. Kilogram per kilogram squared, second squared. So one of those cancels. Now, over here, I'm multiplying by a mass, a kilogram. So I'm going to get VB square root. So I'm going to get, that cancels. I have G, and the kilograms cancel up top, on the bottom. And then I'm dividing by distance. So I get meters cubed over second squared meters. And so that's going to give me square root meters squared per second squared, or meters per second. So the units do work. So that's good. Also, in this calculation, if I increase the mass of the asteroid, I increase the velocity. That makes sense. Also, if I increase the separation, if R1, the bigger R1 is and the smaller R2 is, the better too. Okay, but the problem is that if there is a gravitational force on B, then there's also a force on A. So A also moves. So both of them move. Let's go ahead and rewrite the equation. So I have 0 change in kinetic B plus change in kinetic A plus change in gravitational potential energy. And I'm going to run out of paper. Okay, I'm prepared. And let's just go ahead and put in everything we know. So I already know, I'm going to write this as KB2 minus KB1 plus KA2 minus KA1, 1, plus U2 minus U1. So let's put in all our values. This is 0 and that's 0 because they started from rest. So I have 0 equals 1/2 MB VB2 squared, that's that, plus 1/2 MA VA2 squared, that's that, and then I have minus, I'm going to put this as minus, what did I have? Let's put minus G MA MB times 1 over R2 minus 1 over R1. That's the same thing, right? Because that's the same thing. So that's what I have. And this is the same thing I did before, except before that term was 0 because I assumed it didn't move. But now it does move. Now, if we go back and think about our rocks, we have a force exerted on B, and the same force is acting on A with the opposite direction because this is the same interaction. So if I have the same force on both of them for the same amount of time, well, equal and opposite forces for the same amount of time, they have to have equal and opposite changes in momentum, right? Because F net, and that's the only force, is delta P delta T. So they have the same time, they have opposite forces that have the opposite changes in momentum. So that means that this starts with the momentum of 0, that starts with the momentum of 0. Whatever momentum this ends up with, that has to have the opposite momentum. So let's just write that in terms of, in the x direction, let's say. I could write it formally, but let's just say it's in the x direction. So I'm going to say that MB is moving in the negative direction, but that's fine. VB is negative MA VA2. 2. And if I solve this for VA2, I get VA2 is going to be equal to negative MB VB2 over MA. So this just says momentum is conserved. So now I can plug this in up there. So let's do that. So this becomes 0 equals 1/2 MB VB2 squared. That's the same thing. But now I'm going to square this and put this in up there, and I get plus 1/2 MA, this squared, which is going to be MB squared over MA squared VB2 squared. And you notice I now have two VB2s squares. And then I have this term, minus G MA MB 1 over R2 minus 1 over R1. So what I want to do now is to solve this for VB2 squared. So let's add this to both sides. So it comes over here, or I'll switch, however you want to do it. And then I'm going to factor out the VB2 squared. And so I'm going to do that in one step. So I have VB2 squared times all of that stuff, 1/2 MB plus 1/2. Now you see I have an MA over MA squared, so I'm going to just write that as MB squared over MA. Is that okay? I hope that's okay. I'm just double checking. Yep. And that's going to be equal to G MA MB 1 over R2 minus 1 over R1. So, you could stop here because it's important to realize that this is just, I know everything right here. I know all these numbers. I know all these numbers. So I could just say this is let's say C, some constant, and this is some constant B. I can calculate that, and VB2 squared would be equal to the square root of B over C. I mean, you can simplify this some. You can do that. Whenever I do that, I make mistakes. So I'm kind of like, I don't want to do that. But I guess I could, but I'm not going to, because I don't want to make a mistake. I think the important thing is that I can do that. And I can do it in Python really easily, right? Because I can call this C, I can call this B, and I can put all my numbers and calculate VB2. And let's do that. So let's switch over here to Python. Okay, so back to Python. So let's call this VB2 A, and call that A, just because you could change the value. Now I'm going to say C equals, I'm just typing in my equation right here. I have MB over 2 plus MB squared divided by 2 times MA. That's my value of C. And then B is equal to G times MA times MB times 1 over R2 minus 1 over R1. And then VB2 is just going to be equal to the square root of B over C. I can print that. And this is the new version, so I'm going to print both of them. VB2 meters per second. Now, should it be going faster or slower than the other one? Well, just think of this. If both of the masses are moving, right, they still have the same decrease in gravitational potential energy. So I still have a certain amount of kinetic energy to convert, or energy to convert to kinetic. But now mass A is also moving, so it's going to have some of the kinetic energy. That means less for mass B. So the velocity of B should be less than what it was before. Less than. Okay, so it's not a huge difference. So if you were in NASA and you wanted to calculate the speed, and you said, I'm just going to assume mass A is stationary, it's not bad, right? It's not a terrible approximation. And you could say, oh, it's going super slow. So that's a good place to start. But there you go. That's a better answer. Now, let's do this one more time. And let's do this with force and momentum. Let's do a numerical calculation. So let me just set it up on paper. Okay, so overhead right here. So here's what we're going to do. I like my paper to be straight. So here's A, and here's B. I'm going to calculate the vector R, like that, where R is going to be the position of B, RB, minus position of A, right? Because I'm going to do it in one dimension. It's going to be in one dimension, but it doesn't have to be. So once I do that, I can calculate this gravitational force on A. So the gravitational force on A, F, let's call it Fg, because the gravitational force is negative G, mass A, mass B, over the magnitude of R squared times R hat. So this version of the gravitational force is much better than any others because it returns a vector value. So I'm going to get a vector value. Now, let's use that and assume that I break this into a short time interval. Let's say delta t equals 1 second. That will probably be a long enough time interval, but we can change that. And if this is a small time interval over which this thing's moving, then during that 1 second, F is approximately constant. If that's true, I can say F is the change in momentum with respect to time. I don't have to take a derivative, and I can say that's equal to P2 minus P1. This is just for B. I'm just doing this for B, over delta T. And so I solve that for P2. I get P2 equals P1 plus F delta T. So this says if I know the momentum at the beginning of the time interval, I can find the momentum at the end of the time interval. And then I can do the same thing with the position. I can say V is equal to P2 over M, the momentum, and that's going to be equal to delta R over delta T. So if I do the same thing, that's really R2 minus R1, and this is just for B over delta T. I get R2 equals R1 plus P2 over M delta T. So this is what I'm going to do. That will be just 1 second. Of course, it's going to take a lot longer than 1 second. So I'm going to calculate the value of R, and then I'm going to use that to calculate the gravitational force. And then I'm going to update the momentum, update the position. And I'm going to do the same thing for mass A. Update the momentum, update the position. And I don't need to recalculate the force. It's the same as this, but opposite. And so I don't want to do all those calculations, so I can do them in Python by breaking into short time intervals, and Python won't care. Let's do it. Back to the computer. So I'm first going to make my masses, my asteroids. I'm going to call them A and B. A is just a sphere. It's going to be at the origin. I have to pick that. So I'm using WebVPython, and so it has these built-in three-dimensional objects like the sphere, which is super nice. And I said this one had a radius of 10, and that's fine. We don't need to. I'm going to leave it as grayish asteroid. It's fine. And then B is going to be a sphere. Position equals vector. It's going to be 1. It's 100. Let's call it R1. R1, 0, 0. So R1 is 100. How far apart they are. And it has a radius of 6. Let's just run it. I like to, once I make an object, I want to run it just to see if they're in the right place and everything's working, because you never know when things are going to break. So there's my 2 asteroids. And this is in 3D. You can rotate it around. You could change the lighting and the color and all that stuff, but I don't really care. Okay, now I need to give them both an initial momentum, A dot P. So we can do this property of the object by using this A dot P, and that we can call it, instead of having PA, PB, all that other stuff. And it's just going to be 0. 0 vector, right? I want to start them at rest, so I don't even have to multiply by the mass, although you could, MA if you want. Do the same thing for B. It's going to be MB times vector 0, 0, 0. Now I need the time and the time step. And let's just say 1. Notice there's no units. We don't do units here. Let's run this for 1,000 seconds. So I'm going to say while t is, let's do 500, is less than 500. And I'm going to do rate 10. I don't even know if that's good or not. Let's just run it and find out. So rate 10, if I do 500 seconds, I think that'll be fine. That says don't do more than 10 loops per second in the program. So that would take, each step would be 1 second. That'd take 5 seconds to run one. Let's do 20. Let's do 5. I'm that impatient that I don't want it to run more than a second. So the first thing I'm going to do is to calculate R. R is A.POS, no, B. B.POS minus A.POS. So remember, I need the actual location of these objects, and that is the position property of that object. So I'm using position, B.POS is the vector position of object B. Now I can calculate the force, negative G times MA times MB times norm R. So that's the unit vector in the direction of R. It's a built-in function. Divided by mag R, again, built-in function returns the magnitude of the vector squared. So that's my force on B. Now we can update the momentum of B. B.P equals B.P plus F times et. Now I need to update the momentum of A. A.P equals A.P minus F times et, because the force on A is opposite of the force on B. Now I need to update the positions. B.POS, B.POS plus B.P times et divided by MB, and A.POS equals A.POS plus A.P times et divided by MA. And now I need to update time. T equals T plus dt. Okay, let's run that. And I can't even tell if it's running, so let's just print. Let's go back here and see if it print something at the end. Let's just say I'm gonna print B.POS, the position. Let's just see if it's less than 100 in the x direction. It should move at least a little bit. It's not done. That's weird. Rate T is less than 500. Let's do this as 100. 1,000. Let's just do 1,000. Well, if you can do 100, you can do 1,000. There's no difference. Okay, so it did, and it moved. Okay, so it is moving. Not very much, not very fast. I don't know how long this is going to take. So it's obviously going to take more than 500 seconds. You can't even tell it moved. So let's do this. let's calculate r up here, b dot pos minus a dot pos. And I'm going to change this. I'm going to say while the while the magnitude of r is greater than or equal to r2. Right? So as long as they're further apart than r2, run this. And when it's not, stop it. And then we can go ahead and print out what I wanted to do, right? Print VB2 equals, it's going to be the mag of B dot P divided by MB. That's the velocity in meters per second. And let's do the same thing for the other one. Print VA2 equals mag A dot P divided by MA. And I didn't do this before, but I can. Let's just run it and see if this works. Is it even moving? I think it is. I can tell that's moving, but I want to increase my rate. I think my time step is too small, but that's fine. Okay, that's better. See, now it's moving. Here they're going to crash. This is not moving in real time because it'd really take a long time. And you see, these are my calculations. The first one is my calculation assuming mass A is stationary. The second one's assuming it moves. The third one is the velocity of B using a numerical calculation. And you see they're pretty much the same. Now there is one, and then there's the velocity of, that's the magnitude, the velocity of A. So it's moving too, not as fast, but it is moving. Okay. And let's do one more thing. How long does it take to collide? Let's print that. T equals T. And let's put it in minutes. So let's do T divided by 60, and that'll be in minutes. I think it's going to be a long time. There they go. 557 minutes. 0.5. Okay, so if you wanted to, you can make a graph of the kinetic energy, the total energy as a function of time, or the momentum as a function of time. It doesn't really matter. The nice thing about this problem is that it includes both momentum and energy. You have to use both of those in order to solve the problem, and that makes it kind of fun. So I will give you a link to this code. I'm going to save it right now down below, and I will put a link to my derivation of the gravitational potential energy. Okay.